Hello, I am Zach Pringle, and this is my workshop 2. The problem that we are looking at for the workshop 2 is a video game scenario where we have attackers, defenders, and healers. The players that are all put into an array, which is kind of the queue, and all of the players have to be put onto teams that are either 4 healers and 1 attacker, or 3 attackers, 1 defender, and 1 healer. And the goal is to get the greatest amount of teams possible based on the queue or whatever players are up there. So in this case, if we have like 10 attackers, 10 defenders, 10 healers, there's two best case scenarios, which would both give 4 total teams, and it's either having one team of 4 healers and 1 attacker, and 3 teams of 3 attackers, 1 defender, and 1 healer. Or you could do 2 teams of 4 healers and 1 attacker, and 2 teams of 3 attackers, 1 defender, and 1 healer. So the way I went about solving this problem is I used n as my number of players and t as my number of teams, although neither n or t are actually used since I just used the size of the vector for the number of players and the size of the vector for the number of teams. So I have, in this case, a vector of players, and the size is n, which is just the total number of players in the queue. Then we have a character variable assigned to attacker, which is a, and defender d, and healer h. Then we have another vector of teams, which would be the size t, which is just the size of the number of teams in the vector. And then we display the total number of players, which is just the size of the players vector. Then we're going to set a to use our roll count function, which our roll count function just counts the number of each letter in, like the number of attackers, the number of defenders, the number of healers, and it will set it to A, D, and H. And then we display the number of attackers, defenders, and healers. And then we're going to run the make team function, which will be on the next slide. So the make teams function is kind of where all the magic happens. We have an input of A, H, D, and our 2 arrays. Then we are setting our iterator. And then the way I went about solving this problem is doing more of a ratio. So if A and H, so basically if A over H is greater than 3 over 4, then most of the time I want to try to run the attacker, like the 3 attackers scenario. But obviously H can't equal 0 in this scenario, and D can't equal 0 in this scenario. And if A is 0, this won't run because it would be not greater than 3 over 4 in that case. So we want to run it in that scenario, so we'd run it and we'd have A minus 3 because we want to get rid of 3 attackers. We'd have D minus 1 because we want to get rid of 1 defender, and we'd have H minus 1 because we want to get rid of 1 of the healers. And then we want to drop that from the player's vector. So we use the for loop. We're just using a for loop for the A, so it's faster. You can do all 3 of them. It'll look for the first A in the player's team, and it'll drop that value. It'll do that 3 times. It'll drop the first D, and then it'll drop the first H. And then once we remove the H, we add AADH, so 3 attackers, 1 defender, 1 healer, to the teams vector, and then it'll be a recursive function, so it'll run make teams again, and we'll go back to the top. So then let's say in this scenario it doesn't meet the first criteria, it would go to the second else if statement, which looks to make sure that H is greater than 4, since we need to have 4 healers, or greater than or equal to. Attackers can't equal 0 because we need at least 1 attacker, and H can't equal 0 because we need obviously at least 4 healers. A would equal A minus 1 because we want to get rid of the 1 attacker, and then H would equal H minus 4 because we want to get rid of the 4 healers. Then we do the for loop to drop the H's out of the player's vector, and we do that by running that 4 times, that for loop. And then we drop the A off the end of the player's vector, and then we would add the 4 healers and 1 attacker team to the end of the team's vector, and then we would run the recursive function again, so we'd run make teams again. And whenever neither of those scenarios are true, it will go to the else statement. It'll print final team comp, and then it'll print off the team vector to show all the teams that were made. It'll then print total number of teams created, and that is just the size of the team's vector, so the amount of variables sitting inside of the team vector will just be displayed, and then it displays the players left over. So it'll just display then the players vector, which shows the rest of the players that are still in the queue technically. This would be my coding example in C++ of this scenario. We started off by creating our make teams function, which has the inputs of A, H, D, the vector of players, and the vector of teams. And then we set our iterator. Then we do our if statement of H can't equal 0, D can't equal 0, and our A over H is greater than 3 over 4. Just as an interesting side note, you cannot put the A over H is greater than 3 over 4 first, because if H still equals 0 and it still tries to run that, it'll be an error because you cannot do that as 0. Then we do A equals A minus 3 because we're getting rid of the 3 attackers, H equals H minus 1, D equals D minus 1. Then we run our for loop to drop off the A's from the end of the player's vector, or I guess the beginning of the A's in the player vector. And then we drop off the first H, drop out the first D. And then we do the pushback to push AADH to the team on the back of the team's vector. And then we have the recursive make teams run again if it makes it to the other part of the else state, like the else if statement. We have H being greater than or equal to 4, A can't equal 0, and H can't equal 0. Then we do A is A minus 1, and H is H minus 4, because we're getting rid of 4 healers and 1 attacker in this scenario. Then we run the for loop to drop off the first 4 H's that come up, and we run that function to drop off the first A that comes up. And then we push the 4 healers, 1 attacker to the back of the team's vector, and then we would be running that recursive function again. Then eventually we would get to the else statement, where we have what we like to display our final team composition. We would run the teams for loop to display all of our teams. We would have the total number of teams, which is just the size of the team's vector. We have our players left over, which would then display the player's vector and everything inside of it, because that is whatever's left over in the queue at the end. Next we would have our roll count function, which the main goal of that is just to tell how many of each role, like attackers, healers, defenders, there are. So all it does is count whatever variable, like whatever role gets put into it. So if it's A, it'll count the number of A's, D, it'll count the number of D's, H, it'll count the number of H's. In our main part of our function, we have our vector of team Q, which in this case it contains 9 attackers, 10 defenders, 10 healers as an example. So we have a character attacker A, the defender is set to D, and the healer set to H. And then we set our team comp vector. Then we set our size to the team Q size. So that would be the size of our team vector, our player's vector at the top there. Then we display our total number of players, which is equal to the size. We set A equal to the roll count, so that's how we know how many players, like how many attackers there are. We set D to the number of defenders there are, and H to the number of healers there are. Then we display the number of attackers, healers, and defenders there are at the start, and then we run our make team function, which does the rest of that. This would be the output of my example for my code. We would have total players, it would be equal to 29, and that would be consisting of our 9 attackers, 10 defenders, and 10 healers. Final team composition includes 2 teams of the 4 healers and 1 attacker, and 2 teams of the 3 attackers, 1 defender, and 1 healer. The total number of teams that got created would be 4, and our leftover players would include 1 attacker and 8 defenders. Here we're looking at our time complexity. When we have our vector, and that's theta n, depending on the size n. We have theta 1 for all of our attackers, defenders, and healers being set to their variable. Another theta n for the size of teams made. We have a theta 1 for just the display. We have theta n for our roll count, because that's based on the function, which we'll talk about in a second. Theta 1 for the display, and then a theta n for our make teams function, which we'll look at in the next slide. So for our function, we have theta 1 for set count, we have theta n for our for loop, and then we have theta n for the if statement, and then technically anything inside the if statement can run up to n times, or it could run as little as no times, depending on if there was just no defenders, attackers, or healers in there. And then we return is the theta 1. Here we're looking at our make teams function for time complexity. So we have a theta 1 for our setting our iterator. We have a theta 1 for our if statement, theta 1 for setting a, d, and h equal to their new value. We have a theta 1 for this for loop since it only runs up to 3 times. A theta 1 for anything inside of that, so setting the iterator, checking to see if it's not at the end, and removing the a from the vector. We have a theta 1 for finding the d, finding if it's at the end, and removing it, and then the same thing for the h, and the theta 1 for adding the string to the end of the team's vector, and then a theta n for the recursive call on the function, because it could be called n number of times. Then on the other side, we have our other else if statement, where we have a equaling a minus 1, which is theta 1. We have h equal h minus 4, which is another theta 1. Theta 1 for our for loop, since we know it runs only 4 times. A theta 1 for anything inside of that, so the iterator being set to h. If it's not at the end, remove the h. Then we have a theta 1 for finding our first a, checking if it's at the end and removing it. And then we have a theta 1 for adding the 4 healers, 1 attacker string to the end of the team's vector. And then a theta n again for the make team, because it could run n times. And then we have our else statement, so we have a theta 1 for printing the team comp part, and then theta n for printing the actual contents inside of the vector, since it's based on the vector size, which is n. And then we have the print part below that, which is theta n, because anything inside of the for loop is theta n. We have a theta 1 for the total number of teams created being printed, theta 1 for the size of the team vector, theta 1 for the players left over being printed, and then a theta n for running the actual printing part of the vector for the players, because it's based on like the amount of players left over, which would have been a size of n at some point. Since after looking at all the parts of the functions and the main area, the biggest strain on the time is a theta n. Our total time complexity becomes theta n. Now we're going to look at our space complexity. We only look here when something is being initialized. So in this case, we have our vector here, which of size n, so that's theta n. Then we have just 3 constants in a row, so we have theta 1, theta 1, theta 1 for the attacker, defender, and healers being set. Then we're going to have another vector, which is also going to be a theta n that's being set, and then we're going to be setting a, d, and h in this case, so those are all going to be set to a constant value. Then we're going to look at our function, which sets count here, which is a theta 1, and then we have setting I here, which is a theta 1. The space complexity for the makes team function is fairly straightforward, since we're only initializing a few variables here, since we're, and really it's only the initializing I is in the for loop, so those are all constant theta 1s. This makes our total space complexity a theta n, and that's just based on the size of the vectors that we are creating. For our proof of correctness, we used loop invariant, and after n iterations of the makes team function, we'll have a vector of string player roles or teams that should contain n number of teams, which is going to be the largest number of possible teams made. Our initialization, so at the beginning of the loop, the vectors empty, and A, H, and D are all set to the total number of attackers, healers, and defenders. For our maintenance step, we assume that the iterations stay true during all n iterations, and at the nth iteration, we have a team vector that will contain n number of teams. For our termination step, we basically run this recursive function until it doesn't meet either of our if statements, and in this case our if statements are h not equaling 0 and d not equaling 0 and a over h being greater than 3 over 4, and it also can't be if h is greater than equal to 4, or greater than equal to 4, and a doesn't equal 0 and h doesn't equal 0. If it doesn't meet either of these, then theoretically it has been shown that it'll spit out the highest number of possible teams, and the recursive function now stops. Thank you for watching my workshop 2, and if you have any questions, please reach out to me at pringlesy@umich.edu.